Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakallan. The 56th session of Graph Theory 2. So that is, the topic is results on arborescence. Okay, already we have got a concept called arborescence that we have discussed in the previous class. So now we will see what are the results on this arborescence. Okay. Let me recall an idea which we have already discussed in the previous class, of course. Accessibility. What do you mean by accessibility? If there is an edge from A to B, then B is reachable or accessible from the vertex A. So this is the concept. In a diagram, a vertex B is said to be accessible, or you can say reachable from a vertex A if there is a directed path from A to B. Okay. And what is arborescence? Arborescence is nothing but it is, of course, a kind of a tree. Of course, it is an extension of a tree. This graph or this diagram does not contain any circuit. It may be directed circuit or semi-circuit. But what is the difference between a tree and arborescence? Of course, arborescence is also a tree, directed tree, in which there is one vertex, one and only one vertex of in degree 0. There is one vertex, exactly one vertex, whose in degree is 0. And the in degrees of all other vertices other than the root is 1. So that is the special case. So what we have observed in case of the tree and the arborescence. So arborescence is also a tree, but particularly you will get one root. So the degree of that vertex is in degree is 0. That is called a root. And the degree of every other vertex other than the root, that is the in degree, is always 1. So such a graph is called arborescence. So that already we have discussed in the previous session. So based on the concept of arborescence and accessibility idea, now we will consider one theorem. So the theorem is an arborescence is a tree. Of course, an arborescence is a tree that we have observed. An arborescence is a tree in which the in degree of every vertex other than the root is exactly 1. So this was the observation in the previous session. Already definition is different, but what we have observed in the arborescence, when we observed the degree of in degree of every vertex, root has got in degree 0, but all other vertices other than the root have degree in degree 1, isn't it? So that is the observation what we have observed. So that observation itself is the result. So an arborescence is a tree in which the in degree of every vertex other than the root is exactly 1. So how to prove this result? Very simple result, of course, based on the observation. We try to prove this result. An arborescence with p vertices can have at most p minus 1 edges, because as arborescence is also a tree, so then so if there is a tree with p vertices, then how many edges are there in the directed tree? P minus 1 edges. So here also obviously an arborescence with p vertices can have at most p minus 1 edges. Definitely, at most, maximum p minus 1 edges if it is a tree. Definitely, okay. So therefore, the sum of in degrees of all vertices in G, that is, if you find out the in degrees of all vertices V1, V2, and if you add, definitely what happens? It will be definitely less than or equal to p minus 1. Okay. Now, out of this p terms, one corresponds to the in degree root. Definitely, out of these p terms, one corresponds to the in degree of the root, because root is also involved as a vertex of the arborescence. Therefore, one term is 0. The sum of the remaining p minus 1 terms is less than or equal to p minus 1. Definitely. The remaining terms are positive integers and they must be all ones. Therefore, the in degrees of p minus 1 vertices are 1 each, and in degree of root is 0. So therefore, what you can say, G is a circuit less by the definition of arborescence. Therefore, arborescence is a tree which is grown up from the root. So already we have observed in the diagram, okay, a diagram which we have considered in the previous session. Okay, so there only we come to know by the observation that the vertex which is called a root, which has got in degree 0, and there we have observed the degree or in degree of every other vertex other than root exactly in degree is 1. Okay, so therefore this is a simple proof. We have proved the result very easily. Now we consider another simple result. If every vertex is reachable from a vertex V, see, this is very interesting. If every vertex is reachable from a vertex V, it implies there is a directed path from V to every other vertices. Okay, if you consider any other vertex B, if every vertex is reachable from a vertex V and G has no circuit, then G is arborescence. This is another way of defining arborescence, you can say. Okay, proof. How to prove the result? The root V is not reachable from every other vertex. Why V is not reachable from every other vertex? Because the in degree of a vertex is 0. When in degree is 0, there is no edge which is incident into the root V. So therefore, the root V is not reachable, or there is no any direct path from one vertex to the root V, because in degree is 0. So for that reason, what we can say, the root V is not reachable from every other vertex. So you can say the in degree of V is equal to 0. Then every vertex other than V is reachable from V. Because you can see, so the previous session I have shown you the example of an arborescence. There every other vertex, the in degree of every other vertex is 1. It implies every other vertex is reachable from the root. So what we can say, every other vertex other than V is reachable from V. Therefore, the in degree of each vertex is at least 1. Definitely, when it is reachable, the degree of in vertex must be at least 1. But the in degree of every vertex is not greater than 1. That is also there, because the number of edges in G is P minus 1. So for that reason, the in degree of every vertex won't cross 1. So where P is the number of vertices in the diagram G. So thus, if this is the case, G has only one vertex of 0 in degree and G has no circuit. If this is the conclusion, then what we can say, the degree of every vertex, the in degree is 0, and what we can say, it is circuitless. It has got one vertex whose in degree is 0, that is the root, and there is no circuit at all. It implies this is definitely a directed tree, or you can say therefore G is an arborescence. Okay. So therefore, in this session we have discussed some results based on arborescence. So simple results with a simple proof related to trees and even related to directed path. So we have discussed in this session. So these are the reference books for your reference. With this we conclude today's session. Thank you.